The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you very much. My name is Miguel Vicente, Associate Professor at the Department of Civil Engineering at the University of Burgos, Spain, and my presentation is about a comparative analysis of different technologies to measure the vertical deflection in high-span, high-rise concrete girder viaducts. The aim of this work is to compare different technical solutions to measure a small vertical deflection in some singular concrete viaduct belonging to high-speed rail line in Spain. This singular viaduct shows high span, high rise, and also due to technical requirement to the train, also a high stiffness. I'm going to explain this by showing a particular case we worked several months ago. In Spain, it is mandatory to carry out static loading testing in all bridges and viaducts prior to putting into service. Also, in the case of bridges belonging to high-speed rail lines, it is also mandatory to carry out intermediate static load testing once the infrastructure is finished and prior to the construction of the superstructure, the ballast layer, the slippers, and so on. In this special situation, at this intermediate load testing, the load is carried out using trucks instead of trains, and the expected vertical deflection is quite low. So it is a technical challenge to measure with accuracy this vertical deflection. This is the case study I'm going to show you. This is a viaduct over Tera River. This belongs to the high-speed rail lines, Madrid, Galicia, northwest Spain. It is a post-tension concrete viaduct. The total length is 645 meters. It is a box girder. The main span of the difference span is 75 meters. And as you can see, there is an arch between pile 2 and pile 3. And the main span of the arc is 150 meters. And also the main height of the arc is 60 meters over the river. The project was carried out by Carlos Fernández Casado Engineering Studios in Spain. The contract manager was Acciona, and the ownership is ADIF. This is the public company belonging to the Ministry of Public Works. Several load cases were performed, and the maximum state, the number of trucks used were 30 trucks, and the unit weight of each truck was 40 tons. So the maximum applied weight was 1,200 tons. In all the load cases, we put the trucks on the deck, and we remain the trucks on the deck during at least 10 minutes. We have to measure the vertical deflection once the truck are placed on the deck, and 10 minutes later in order to verify that there is no significant variation of the vertical deflection during these 10 minutes, so we can verify that the structure is sure and this load level. At this particular case, the theoretical vertical deflection to the main span under this load case situation you can show on the screen was 30 millimeters. So the maximum allowed variation of the vertical deflection according to the Spanish regulation during the ongoing stage is 5% of the measured vertical deflection. So the expected variation of the vertical deflection during these 10 minutes was 1.5 millimeters. So our technical challenge is to measure with accuracy enough 1.5 millimeter in this bridge, considering that we are over a river and at 60 meters high. There are several commercial and technical solutions to measure vertical deflection in bridges. We are not going to expose one of the most important I've considered in order to validate if they are useful or not for this particular case. First one is the use of digital level. It is a very, very common solution in bridges in Spain. In this particular case, it's providing enough accuracy. The measurement error using standard high-level equipment is 0.3 millimeters. So it is enough for our requirements. It is a low and medium cost solution, so it is okay in this aspect, and it is not necessary to access the bottom of the viaduct. It is very important in this particular case. The main disadvantage is that it provides a discrete measurement. That is a particular problem because Spanish regulation say that in the case of bridges belonging to high-speed rail lines, it is necessary to perform the load testing using a continuous measurement equipment. So in this case, we use the solution as the reference value to measure and to compare to other solutions. It is also a slow process and depends on environmental conditions, especially if not possible to carry out the load testing during night or with intense fog and so on. Another conventional solution is the use of displacement transducers. The conventional setup of this solution is to hang a weight under the bottom of the deck, and we place the sensor on the ground, and the ground is considered as a fixed reference. So the vertical deflection of the deck provides a vertical movement of the weight, and the sensor measures the variation of this vertical position of the weight. So this is the principle of working of this solution. The main advantage is that provide an excellent accuracy. The measurement error is even below 0.01 millimeter. It is a low medium cost solution, so it is able to use, and also it provides a continuous measurement. The main disadvantage is that the maximum recommended vertical distance between the interface of the deck and the ground is around 30 meters. Greater distance provokes that the environmental conditions have a very strong influence on the results, especially wind and also temperature variation. Another disadvantage is that it's necessary to access the bottom of the viaduct, and in this particular case it is not possible because of the river. Another possibility is the use of laser distance meter. The conventional solution is to place the distance meter on a tripod on the ground, have a target on the bridge, and we measure the vertical variation of this target. The main advantage is not necessary to access the bottom of the viaduct. In fact, it is not to access the vertical shadow of the viaduct, and the maximum measured distance is more than 150 meters. So it is a potentially useful solution. Also, it's possible to obtain continuous measurement. And the main disadvantage is that the accuracy, we are at the frontier of the accuracy with this solution. It strongly depends on the environmental conditions. The measurement error varies from 1 millimeter if there are extremely favorable environmental conditions to more than 2 millimeter, even to 3 millimeters. And it is also a medium high cost dependent solution. Another solution that we have discarded was, for example, GNSS solution, because of the accuracy was extremely bad for this particular case. The given error for vertical measurement is around 20 millimeters, and it's not possible for us to use this solution. Another solution is the vision-based displacement system. It is an emerging, a very promising technology. But the main advantage is that it's not necessary to set the bottom of the viaduct, and also it provides a continuous measurement. But today, the main disadvantage is that for this particular case, that it not provide enough accuracy, and the measurement error was even greater than 5 millimeters, and it's also a high cost, in fact, a not mature technology. So we discard this solution for this purpose. So we need to develop non-conventional solution using conventional sensors, but carrying out in different form. In this case, the technical solution we used was to establish an internal fixed reference inside the deck. To use it, we developed a V-shaped structure. It was fixed at the diaphragm, placed at the arch and also at the pier. So there was no vertical movement. At the target section, a weight was placed. Also, the steel wires were fixed to the diaphragm at the neutral axis of the section, so eventual rotation of this section to vertical loads that not provokes vertical movement of the weight. So here we can see the V-shaped structures, also the weight and the sensor inside the deck. The steel wire was tensioned using a wire tension, and the weight is placed at the target section, as we have mentioned before, and this displacement sensor is placed under the weight. Here we can see the connections on the red line. On this one, it was a conventional connection, and this other one was the wire tensions. The main idea of this solution is that during the load testing, the fixed reference remains fixed because not vertical movement of the weights. Of course, due to the vertical loads, there is a vertical movement of the deck, and also there is a vertical movement of the sensor placed on the deck. So the sensor measures the variation of the distance between the inner slab, the lower slab of the deck, and the weight. In this case, we use different displacement sensors to measure and to compare the results. We use potentiometer and displacement transducer, conventional one with internal springs, potentiometer displacement transducer without internal springs, LVDT with internal springs, and also a non-contact solution, laser distance emitter. We detected our fixed reference was not real a fixed reference. A contact sensor provides a variation of the vertical position of the weight and induce an error in the results. Here we can see the set V-shaped structures and sensor from a mechanical point of view. So V-shaped structure is an elastic structure, so it can be drawn as a spring. And also, in general, the sensor, the contact sensor, has an internal spring, so it's providing an elastic behavior of it, and also it provides a plastic behavior due to internal friction. When a vertical displacement of the sensors occurs, it is equivalent to applying a vertical force to this structural system. And of course, due to the stiffness of the V-shaped structures, there is also a vertical movement delta 1 of the weight placed there. The sensor does not measure vertical deflection, but the difference between vertical deflection and the vertical deflection of the wave, delta 1. So there is a certain error on this one. So it depends on the different contact sections. The different contact sensors provide different error. In case the worst one was the potentiometer displacement with internal spring because of also internal frictional effort and also springs occurs. And the best one is, of course, the laser distance emitter because this is a no-contact technology, so it don't move the weight. Okay, for this particular case, the digital level, the data acquisition speed was 1 data each 2 minutes, and the laser distance meter, we obtained 1 data each 10 seconds, and additional filtering process, we obtained the average value at each 30 seconds period. Also potentiometer and LVT, 1 data each second was collected. This is finally the result of a load case. Here we can see when the tracks are on the deck, and also this belongs to the residual deflections. This is a detailed view of the on-weight state. As we can see, this is the digital level as the reference. The laser distance emitter provides a quite close to digital level value, vertical value, and also the contact sensors provide lower value. The variation is between 1 minute. So the conclusion is that the measurement of the vertical deflection of viaduct belonging to high-speed trail lines is not an easy task because of they show high span, high rise, and as a consequence, and also high stiffness, and as a consequence, low value of vertical deflection. Additionally, it is necessary to evaluate the variation of the vertical deflection during the on-weight period of time, then it becomes a technical challenge. The stiffness of the fixed reference provoked that both potentiometer and LVDT, all the contact sensors, measure lower values of vertical deflection than real, and on the contrary, laser distance emitter provide a very good solution. Thank you very much for your attention.